welcome you all to this course on electron diffraction and imaging. In today's class, we will talk about how to index planes in hexagonal system. Two important classes, most of the structural materials, if you look at it, either they have cubic crystal structures, either BCC or FCC structures, or we have another class which is essentially hexagonal structures, especially most of the zirconium based alloys or titanium based alloys. Okay. In crystallography, when we try to represent the crystals, we essentially use 3-index coordinate system. Okay. That is how we represent the crystal structure, correct, including all the 7 classes which are there, including hexagonal crystals. Okay. Especially if we take with respect to structural materials, okay, cubic system or the other one which is zirconium or titanium based alloys or magnesium based, okay, there are lots of alloy systems are there which are essentially having a hexagonal crystal structure. Okay. We use a 3 coordinate system, okay, to represent the crystal structure, and the planes are represented using HKL. Okay. We know how to find out the planes, but what happens is that in such a system for cubic crystals, when we represent a plane, okay, specific one as 110, if we represent a plane, okay, this is a specific plane, and if we represent the family of planes 110 with a curly brackets, this means that all the other planes are related by symmetry. But what happens in the case of a hexagonal system is that indices what it represents and the symmetry, there is a disconnect. This we can look at it if you look at this figure which is shown here. Okay. That is in a hexagonal lattice. I will just show the basal plane alone. Okay. This is the x axis, y axis, and the z axis is normal to it. Okay. The angle between these is 90 degree. Okay. Then this plane will be an 100 plane, correct. This plane is 010 plane. If we take this plane in this system, this is going to be 110 plane, correct. How do we find out these planes? By first finding out, okay, take that plane, find out what is the intercept which it makes with respect to the axis, okay, take the inverse of it, okay, and then try to, so if it is a fraction, okay, multiplied by a number so that it is not in fraction, okay, and remove the common factor otherwise, so that that represents the indices of the plane. For example, if we take the 100 plane, in the case of 3-index system, this will turn out to be along the x axis intercept is 1, on the along the y it is infinity, the intercept it makes infinity. So, this will turn out to be 100 if we take the inverse of it. Okay. I am taking it with an example because that is the easiest way to understand. And then if it take with respect to 010, again it will become 0, no, infinity, then 1 infinity, for which it will turn out to be 010, correct, and here it will turn out to be 1 minus 1 infinity, which will turn out to be 110. Okay, this is the intercept. Okay, this is what we call it as a Miller indices, correct. But with respect to a hexagonal system, all these planes are similar type of planes, correct, but they do not have the same indices are not used to represent when we use 3 index system. So, it becomes quite confusing. Okay. How to overcome this? Okay. That is what essentially it is. For which what is done is that since in a hexagonal system there are along the basal plane there are 3 symmetry axes are there. Okay. We use with respect to all the 3 axes. So, x, y, okay, and this we can call it as an I, and this axis is going to be the z axis. Okay. That way we can represent it. If we represent it that way, okay, then now let us look at these planes. Okay. The same methodology which we adopt in the case of a 3 index system to find out the Miller indices, let us do. Now what it will happen is that it makes an intercept 1 here, this is for 1 0 0 plane, okay, which is in a 3 index system. Intercept which it makes it is 1. With respect to the y axis, it makes an intercept which is infinity. With respect to the this axis I, the intercept which it makes it is again -1. With respect to c, it makes infinity. Now, if we look at it, take the inverse of it, this will turn out to be 1 0 1 bar 0, correct. It is straightforward, it comes. Similarly, if we take with respect to 0 1 0, then this will turn out to be, in the case of x axis, this makes an intercept which is infinity because it is parallel to it because of that. Then with respect to 1, with respect to z, it is going to be -1, okay, then infinity. Now, if we look, this will turn out to be 0 1 1 bar 0, correct. If you see with respect to 1 1 bar 0, because in a 3 index system this has a different indices, so this does not truly represent the symmetry. By looking at it, we are not able to make out. Now, if we see it, here the indices which it makes with respect to x, okay, intercept is 1, with respect to y, the intercept is -1, correct. Then with respect to this axis, it is parallel to it, so infinity. The other one with respect to c, it is infinity. Now, it turns out to be 1 1 bar 0 0. Now, if we look at these coordinate system in the 4 index coordinate system, you can see that only that indices are positions are changed, so that symmetry is being revealed with respect to this. Okay. That is what it happens. And another thing which becomes is, in a general case if we consider it, okay, before we go to a general case, let us look at what it happens. This, suppose this indices is h, k with a conventional one, suppose we represent this as I, okay. Then what is going to happen? H plus k plus I equals 0 in all these 3 cases, correct. So, if we represent any crystals, okay, hexagonal crystal in a 3 index system, HKL is the one which is used to represent the plane, okay. Then in the 4 index system, the same planes are represented HK, I, L, okay, where I turns out to be minus of H plus K, okay. This naturally follows when we just choose the axis, it is as simple as that. Generally in the book they will say that this is the way it is written, but it is a natural way in which we are trying to derive the Miller indices, whatever the method which is being given, it is valid for whether it is a 4 index system or a 3 index system, okay. From this relationship comes, okay. This is generally called as this type of indices are called as Miller-Bravais indices, Okay. This is clear? Okay. This is as far as the planes are concerned. So, this way we can represent all the planes, okay. From 3 index system we are convert to 4 index, or from 4 index system we can convert it to 3 index. Similarly, quite often we have to represent the directions as well. Okay. How do we represent the directions? Generally the indexing which is used is that if u, v, w are the ones which we use to represent the indices of the directions in a 3 index system. Okay. In a 4 index system we write it as capital U, V, T and W. This is how this is represented. Okay. Now, like in this case we have to find out what is the relationship between the coefficients in the 3 index system, and so here if the axis the we represent it as the each unit as into A, okay. Here if we represent B, and this if we represent it as T, okay. And then the other one seems to be C. So, it will be essentially A, B, C, correct. Here it will be A, B, T and C. This is what it is going to be the translation vector in these directions. Okay. But what is essentially important is that now we know that irrespective of the which coordinate system which we use to represent it, the vector has to the value has to remain that same. So, we know that R will be equal to, okay, if you try to represent it as R will be equal to U into A plus V into B plus W into C, correct. In the other coordinate system it will be U into A plus V into B plus T into T plus W into C. Both are equal, correct, is what it is. If we look at this coordinate system which we have chosen, one thing which becomes, if this is A and this is B, this vector if we see A plus B, if we take it, this turns out to be minus T, right. So, now we have that other relationship is that T equals minus of A plus B, correct. We substitute this onto this equation, okay. Then U into A plus V into B minus of A plus B into T plus W into C it will come, okay. Now, we have A, B, C are there, we can find out the coefficients of A, B, C, okay, and that will give rise to what is going to be that expression, okay. This expression will turn out to be U equals U minus T, V equals V minus T, okay, W equals W. This is how it will turn out to be, okay. Now, what is important is fine, we should know what is T, what is the relation to which it is related, okay. This is something which I think in mathematics it is quite often done when we do not know another unknown. Is one of the simplest thing which we can take it is these coefficients which are there, U plus V, okay, plus T, this can be taken to be equal to 0. This is one of the things which it is an assumption. There are many ways in which it can be done. Let us not bother about all these things. The simplest case we take it. If we make this assumption, then T will turn out to be minus of U plus V, correct. This is the only place we have learned mathematics, otherwise all of them are coming out as a natural consequence of the crystal structure itself, correct. We have not done anything. Now if we substitute T with respect to this, okay, and now try to find out what it will turn out to be. U will turn out to be u plus V, small v will turn out to be u plus 2v, okay. T equals minus of u plus v, okay, or W equals W. This is what the expression which will turn out to be. This is now we have represented, or we can write W equals W. That means that we have represented the 3 index system coordinates of the direction with respect to 4 index coordinate system we have represented. Suppose we wanted to do the other way around, 4 index system if we have to do it, okay. It is just solving these equations which are there, all these 4 equations. If you do that, I will just write the final expression what it turns out to be, okay. This one can work out on itself and try to find out. V equals 1 by 3 T equals W. This is what essentially this expression will turn out to be, okay. This one can just since these equations are there, we can just substitute it and solve it. It is very simple, okay. Using this expression we can find out. That means that these equations can be used to find out in the 4 index system any direction which is being given by u v w, okay, what will be the coefficients of u v t w, okay, in terms of 3 index system we can find out, okay. Let us take a simple example, okay. Suppose in this direction, if we see it, it is 1 0 0, correct. For this direction, okay, suppose we wanted to calculate, let us substitute this, okay. U is v and w are 0, okay. So what it will turn out to be, u will turn out to be 2 by 3 in this case, correct. V will turn out to be minus 1 by 3, T will turn out to be minus 1 by 3, W will turn out to be 0, okay. Now if we write this, this will turn out to be this vector, if we write 1 by 3 into 2 minus 1 minus 1 0, okay. That is 1 0 0 direction, the magnitude, this turns out to be this vector. Or 1 0 0 direction is nothing but 2 1 bar 0 direction, okay. So compared to planes, if you look at it, indices change a lot, okay. Using this method we can find out indices of directions in 4 index system when we know indices in 3 index system. Is it clear? Okay. Now generally when we use the another one is formula which we use is the Sohn law. The Sohn law essentially what we write, Sohn law is nothing but HU plus KV plus LW equals 0, okay. This is the 0th order Sohn law which we consider it. So where HKL are indices of planes in 3 index system, right? And UVW are the corresponding direction, correct? So, essentially what it means is that HKL represents the indices of the planes, okay. So, that means the direction which is perpendicular to that plane, this is normal to it, that is what the physical meaning of this. So, if we want to substitute for UVW, okay, what will happen in the 4 index system, okay. Now, what we can do it is that this is the expression for U, V and W. If we substitute this, okay, what it will happen? H into U minus T plus K into V minus T plus L into W, this will turn out to be 0, correct? This will be nothing but HU plus K into V, okay, plus minus of H plus K into T plus LW equals 0, correct? What is minus of H plus K? It is equals I, right? That is I into T plus L into W equals 0. So, exactly a similar expression you get it in Sohn law is identical, whether it is a 3 index system or a 4 index system, the same way it will turn out to be, okay. Then the other one which we will require is that when we wanted to index diffraction pattern, there are so many directions, so many reciprocal lattice vectors which we see, okay. The indices of the reciprocal lattice vectors, how we index is nothing but they are indices of the planes, okay. If we wanted to find out the direction perpendicular to it, okay, or we can consider it in another way, that is we have 2 planes are there, okay. These 2 planes will have a common direction in which they will be meeting, okay. If they meet, how will we find out the indices of this direction, okay. Suppose the planes are given in a 4 index system, okay. We wanted to find out the direction in a 4 index system, common direction. The way in which we can go about is convert each of these planes into 2 index system, okay, and then try to find out using the Sohn law what is going to be the directions corresponding to that, okay. And then when you know the direction, using this formula we can convert it back into a 4 index system, okay. The same thing is done is given in this slide also. Here what has been done is that the planes are given, it is given in some formula which one can directly use it, okay. That is HK and L, this is for one plane. So, what what it means is that H1 plus 2K1 and this here U, V, W are mentioned, okay, directly. So, to find out U, you take a product of this and take a product of this will turn out to be, what it will turn out in that case is that U will turn out to be H1 plus 2K1 into L2 H2 plus 2K2 minus L2. So, similarly we can write expression and we can get it. That is what essentially this sort of a table which represents, okay. Similarly, suppose you are given 2 directions, okay, in a 4 index system. you wanted to find out the planes which contains that direction. Okay. We can use this expression which is given here, okay, this table. Okay. It is exactly the same way. H will be equal to, you multiply this by this one, this term by this one, okay, add them together, you will be getting the value of H. H, K and L, if we know, H plus K equals I. So, we have that 4 index plane system. This is the way it can do. The other way, as I mentioned earlier, we can do it, convert these directions into a 3 index system. That is exactly what it is. It is only the final expression which is given in a form memogram which you can just remember and use it. Okay. This is the way in which we can convert from 3 index system to a 4 index system. From this example, you can make out that this is 1 0 0. Similarly, 0 1 0 also we can find out, okay, and similarly this will turn out to be, okay, this you have to just verify it, maybe 1 bar 2 0, I am not sure, but you can do it. Similarly, the direction 1 bar 0, it will also be turning out to be in terms of this, because this is the 3 coordinates x, y and I which you have chosen, they are symmetry related. So, they will have the same type of an indices which will happen. Okay. This one can work out as an exercise and verify it. Okay. This is the way in which most of the crystallography work, or when we wanted to index diffraction pattern, okay, we can do it. This, when you work out a lot of examples, one will become quite familiar with it, because in the textbook as well as in many of the research papers, when you go through them, you will always see that they use a 3 index system very frequently. Okay. This only through experience one can understand quickly how that system is being used. Okay. Another one which is being done is that quite often this is to how to represent in a 3 index system to 4 index system, how hexagonal crystal system is to be represented. Another way in which a hexagonal system can be represented is in another way of 3 index system, because in this case what we considered as the unit cell, if we consider it, this is A, this is B and the C will turn out to be in this direction, the angle between them is 120 degree, correct. There is another way in which it can be represented is that in any hexagonal system, if this is the way A and B, okay. Another way in which we can represent it is, this can be represented in this particular way, this can be A, this can be B, this can be the C axis, okay. And as an orthorhombic unit cell also, because we know that the unique cell is not unique. Generally we use a unit cell which represents the full symmetry of the lattice. The best example which we can take it is, if we take a cubic system, the primitive unit cell of the cubic system is trigonal, that does not represent the full symmetry. That is why we choose either a simple cubic or body centered or face centered unit cells which we use to represent them. Here we can use a crystal which is for convenience, if we consider it, this is an orthogonal 3 index system with which one can work. Where it becomes very important is, suppose on a hexagonal lattice, okay, an ordering has taken place, and because of that ordering the atom positions have shifted slightly, okay, then it is no more hexagon, it can be a orthorhombic structure. So, in such cases, okay, we can use the orthogonal unit cell to represent it. Even for a hexagon this can be represented, because and on similar lines here essentially from one 3 index system to another 3 index system. Okay. This aspect of it I will take it up in the next class. Similarly, and another one which will happen is that trigonal, if you take it, okay, trigonal system also it is essentially a stacking of hexagonal layers one on top of the other. That is as a general sense, if you look at it, all the cubic system, trigonal, hexagonal, they are all arrangement of hexagonal 2-dimensional lattice, one on top of the other, keeping some distances, okay, in some symmetry positions. That is how these lights are. So, all of them can be represented in terms of hexagonal unit cell, especially in trigonal. It can be represented either on a trigonal coordinate system, or it can be represented on a hexagonal system also, because in material science when people work on many of these compounds, okay, one will find that many of them are either in a rhombohedral structure, okay. Those structures, when we have to represent them, okay, what is the type of indices which we have to use to represent them? That is where sometimes we will use trigonal itself. In some cases it can be indices in terms of hexagonal lattices. These are all the way in which it can be done. Okay. So, essentially in today's class what I have just showed is how to go from one crystal structure from one indexing system to another indexing system, which is the cubic that is the 3 index system, which is normally used to represent all the crystals. Okay. But generally when we use this sort of indexing system, if the indexing system also is chosen in such a way that it represents the symmetry which is associated with the crystal, okay, then just looking at the indexing the planes, we can tell that this belongs to this sort of planes, correct. That is the advantage it is there. That is the primary reason which motivated to go from 3 index system to 4 index system for hexagonal crystals. Okay. I will stop here now.